Hello and welcome to this video. This is the third lesson in the Electrochemistry unit for following the Alberta curriculum in Chemistry 30. So what we're going to be looking at in this video is the topic Redox Stoichiometry. So first of all, just a quick review. Stoichiometry is something you learn in Chem 20, and it's essentially used when you want to find the relative amount of one substance and you're given the information about another substance. So it's used to predict the quantity of something involved in a chemical reaction. So we need a balanced chemical equation to do a Stoich calculation. Now in Redox Stoich, that balanced chemical equation comes from our net redox reaction, making sure we're balancing it based on the transfer of electrons. Now a quick review in how to complete a Stoich calculation. So after you write the net redox reaction using your data booklet, as we learned in the last lesson, you're going to find the moles of your given with either mass over molar mass or C times V. Then you're going to find the moles of your wanted using moles wanted equals moles given times wanted over given. The wanted and given are the balancing coefficients. Then you're going to find the final answer of your wanted species, whether it's mass, concentration, or volume, using the following formulas. So let's get into some examples. Example 1. What mass of zinc is produced? So we don't have zinc to start. It's going to be a product. Remember, when we're doing these questions, we list everything as a reactant. That's what we have present. So it says we're taking chromium metal, or chromium by itself, which implies chromium metal, which is Cr solid, and putting it into an aqueous solution of zinc sulfate. So we have a source of zinc ions and sulfate ions, okay? And water, because aqueous again means it's dissolved in water. Now, after we list what we have present, we identify everything in our data booklet as an OA or an RA. Again, OA means oxidizing agent, RA means reducing agent. When you check on your data booklet, you're looking at the one that is present on the left-hand side of the chart on page 7 as your OA, and the one on the right-hand side is your RA, okay? We have sulfate ions, which are an OA with water, and water again is on both sides. Then you pick the strongest oxidizing agent. That's the one closest to the top on the right hand side, and your strongest reducing agent, the one closest, did I say that right? The strongest oxidizing agent is the one at the top on the left hand side. The strongest reducing agent is the one closest on the bottom on the right hand side. And then you write those reactions. So my oxidizing agent is going to gain electrons and undergo reduction. So zinc 2+, I'm copying this just from the data booklet on page 7, plus 2 electrons, it's gaining 2 electrons to produce zinc solid. My reducing agent reaction that's going to lose electrons undergoing oxidation is my chromium metal. I copy that from the data booklet, but I copy it backwards, right? We're copying it starting on the right-hand side. We copy it over to the left-hand side. On the paper, we write it in the proper order, but copying it from the data booklet looks like the reactants are the products and the products are the reactants, because we're trying to show the electrons as a product. If something's losing electrons, the electrons are a product. So chromium will lose 2 electrons to make chromium 2+ in the oxidation process. Now, this is where the balancing coefficients come from. Do the electron transfers balance? And they do. So that means I don't need to multiply either of the half reactions. I only have 1 mole of zinc ions reacting with 1 mole of chromium solid. Do you have to put the ones? No. But I'm going to, because for stoichiometry, you need balancing coefficients. If there is no balancing coefficient, it implies 1, but I like to show it. Okay? This is a spontaneous reaction. Don't forget to include spontaneity when you're writing the net redox reaction. So that's our reaction. Now we're going to do the stoich part. So it's asking for the mass of zinc produced. So the zinc solid product is my wanted. I always label my wanted with a W. It says I have 100 grams of chromium being placed into my solution. So my chromium solid is my given, and I label that as a G. Now, I am given the mass of the chromium solid, 100 grams. Whenever you're dealing with masses, right away you can get molar masses as well, because you're going to be using the formula mass over molar mass, which uses molar mass. So chromium's molar mass is 52.00 grams per mole. Zinc's mass we're going to look for, so we're also going to write down its molar mass while we're there. 65.41 grams per mole. Remember, if there were balancing coefficients other than 1, that would not affect your molar mass. I'm going to put a little line here to separate these two, just to help me for organizational purposes. So my next step is to find the moles of my given. I'm going to find that with mass over molar mass. So I take my 100 grams, I divide by my 52.00 grams over mole. Now, when you have a denominator, in the denominator, it actually moves up to the numerator. I'm talking about the unit mole, because it's gram per mole in the bottom here. The only reason I mention that, you'll see me when I do calculations, put the mole up here. And the reason I'm doing that for unit analysis, understanding that my grams cancel, I'm left with moles on top. Whatever you're solving for, in this case I am solving for moles, that unit that you're solving for should always be left on top. Okay? So 100 divided by 52 gives us a given moles of 1.923, so on. I'm not writing the whole number down. I'm going to write ... and use the entire long number in my answer to continue in the next step. So now that I have the moles of my given, I can find the moles of my wanted. I take this, again, unrounded answer, 1.923 so on moles, and this is where I apply my balancing coefficient, the one in front of wanted over the one in front of the given. So wanted over given. In front of my wanted, there's a 1. In front of my given, there's a 1. So it's 1 over 1 in this case, wanted over given. Okay? So the moles of my wanted are going to be the same number, unrounded again. Now I can find my answer, which is mass, with moles times molar mass. So the moles I've just found, unrounded, times my molar mass, 65.41 grams per mole. So my moles cancel and we're left with grams on the top. I'm going to have to write really small here. So my unrounded answer times 65.41 gives me an answer of 125.78 so on grams. If we look back at the question, there's 3 sig digs, so I need to round this to 3 sig digs, which would be 126 grams as my final answer. Okay, 126 grams. Let's move on to the next example. So the next example is a solution, 2 solutions actually. We are taking a solution of potassium permanganate and reacting it with an acidified solution of iron 2 sulfate. Okay, so if I list everything that I have present, we have potassium ions permanganate ions. You always have ions when you have an ionic compound that is dissolved in water. Acidic environment for the other compound, the other solution, means we have hydrogen ions present. And the other solution, again being ionic, means I have a source of iron dissolved ions and sulfate dissolved ions. And I have water. So there's my listing everything. Now again, we're finding everything on the data booklet on page 7. If it's on the left-hand side, it's an OA. Permanganate is a very strong OA as long as hydrogen ions are present, and they are. Hydrogen ions by themselves are an OA. Now, don't forget, if you paid attention in the last lesson, or you can rewatch that if you need to for predicting a reaction, some ions with a 2+ charge are on both sides of the chart. Fecursin. Okay? Those ions are on both sides, the OA and the RA. And the reason that's important, if you forget that iron 2+ can also be an RA, that's actually your SRA, your strongest one. Okay, so you will write the wrong oxidation half reaction. If you identify Fe as only a OA, you're going to think water is the SRA. And in fact, it's the iron 2+, that's the SRA. Okay, and my SOA is permanganate with hydrogen. So my oxidizing agent that's going to gain electrons undergoing a reduction reaction is permanganate. So if I copy that half reaction from the data booklet, my permanganate reacts with 8 hydrogen ions, and it gains 5 electrons in this process. And it is producing manganese ions, which are colorless. This is important. We're going to be looking at titrations in this lesson. And this is a very common titrant that we use, because permanganate is purple in color, but when it fully reacts to make manganese, it turns colorless. Okay? So that's going to come up when we talk about titrations in a minute. Now my other half reaction, my reducing agent that's going to lose electrons and be oxidized, is the iron 2+. When iron 2+ loses an electron, it forms iron 3+. That again is being copied from the data booklet on page 7, copying Fe2+ on the right-hand side of the chart, copying it towards the left-hand side. So that's where it forms Fe3+ and loses 1 electron. I could put a 1 there to remind me that's 1 electron. Now, balancing electrons. I have 5 and only 1. That doesn't balance. So I have to multiply this reaction by 5 so that my electrons balance. Everything gets multiplied by 5 in that reaction. So now my electrons balance, and my net redox reaction, which is a little bit long, so I'm going to write this a little smaller. So I have 1 MnO4 and 8 hydrogen ions. And you don't have to underline the balancing coefficients either. I just like to do that for stoich, because again, those balancing coefficients are used for wanted or given. I have 5 Fe2+. I am producing 1 Mn2+, which again was colorless, and 4 water molecules, water also being colorless, and 5 iron 3+. I'm going to run out of space here. Now don't forget spontaneity, always whenever you're writing a redox reaction. And you'll notice for redox stoich, the reactions are spontaneous, because if you're asking how much reacts, how much is produced, whatever the question's asking you for, the reaction isn't happening unless it's spontaneous. So they all for redox stoich will be spontaneous. But double check, obviously. If your OA is above your RA, it's spontaneous. So it's asking for the volume of potassium permanganate. Now what in my net reaction comes from the potassium permanganate solution, or what's left in the net reaction of the potassium permanganate solution, and that is the permanganate ions. So I want to find the volume of my permanganate ions. The concentration's given 1.50 mole per liter. Okay? Then it's saying we're reacting 500 mils of 2.25 mole per liter acidic iron 2 sulfate. I'm not dealing with a specific acid here, so this is not about my acid. This is about my iron 2 sulfate solution, the concentration and volume. And what's left in the net ionic equation of the iron 2 plus sulfate is the iron 2 plus. So this is my concentration and volume of my iron 2 plus. Okay, the volume needs to be put into liters, and the concentration is in the units it needs to be. So now I have everything identified. The only time you're using the H, the hydrogen ions, as a wanted or given is if it tells you specifically the concentration and volume or volume of the acid. So it says this is the concentration volume of sulfuric acid, for example. Then you use the hydrogen. Otherwise, you're using the other ions. Okay? So to find the moles of our given, we're going to use C times V. So our concentration is 2.25 moles per liter. And I'm going to multiply that by my volume, 0.500 liters. So my liters cancel and we're left with moles. So 2.25 times 0.5 is 1.125 moles as my moles given. Now I can use that to find the moles of my wanted. I take the moles given that I just found and multiply by balancing coefficients, wanted, which is a 1, over given, which is a 5. So I'm multiplying by 1 over 5. And we get the moles of our wanted to be 0.225 moles. Now I'm looking for the volume of my wanted. So volume is found with N over C. So now that I have my N of my wanted, I divide by the C of my wanted, which was 1.50 moles per liter, makes the liter up there. My moles cancel, and I'll get left with the volume in liters. We get 0.15 liters, and we need 3 sig digs. Leading zeros don't count, so I have to add a 0 to the end. And that's my answer, 0.150 liters. Or if you want to put it into milliliters, you don't have to, but it would be 150 milliliters. Okay? Now let's get into titrations, which is my favorite part of this unit. I love doing titration experiments. I hand this sheet out to my students to remind them of the different pieces of glassware that they use throughout different labs in the course. But in a titration experiment, specifically, we're using things like burettes, Erlenmeyer flasks, pipettes, burette clamps, and so on. So this is a nice image of a titration setup. We have a burette, which is right here. The burette holds the solution that we call the titrant, and we have an Erlenmeyer flask that holds the other solution that we call the sample. Okay? Now, what is the purpose of a titration? The purpose of a titration is to find the concentration of an unknown solution. All right? And the actual purpose, not purpose, but in the process of the lab, that helps you find the volume needed for them to fully react with each other. You have a known volume that you're pipetting into the Erlenmeyer flask of your sample. The burette has increments on it, and it's going to tell you what volume you're adding to react fully with the sample. Now, the titrant is always going to be the oxidizing agent, and there's two that we use that we'll talk about based on their color. and the sample is going to be the reducing agent. The endpoint when the reaction has gone to completion is indicated by a color change. Now we do titrations in Chem 20, but with acids and bases, and we would use indicator solutions to help us identify at what pH that endpoint is reached. This is not an acid-base titration, this is a redox titration. And so our indicator is actually the titrant itself. The two titrants that we use are either potassium permanganate or a source of dichromate ions. Permanganate ions because they're purple and dichromate ions because they're orange. And the reason they are the indicators in our reactions is because, as I showed you in that last reaction, permanganate is purple, and as it reacts, it turns into manganese, and manganese is colorless. So as long as the permanganate ions are continuously reacting with whatever the sample is, it's going to turn it colorless, the reaction is continuing to happen. But as soon as the reaction is complete, you will add 1 drop of excess permanganate, and that'll turn the solution usually a really light pink color. Okay? So the volume of the oxidizing agent is called the equivalence point. And we do again these experiments to identify the concentration of an unknown solution. Now, solutions like permanganate and dichromate, their concentration changes daily. So if I'm trying to find the concentration of a solution like hydrogen peroxide, which is what we do a lab in Chem 30, we have to first find what the concentration of the permanganate is before we can then use it to find the hydrogen peroxide. So the lab that we do in Chem 30 is a 2-day lab. The first day we use a primary standard of an iron solution to find the concentration of the permanganate. Then the second day, now that we know the concentration of the permanganate, we can react it with hydrogen peroxide to find the hydrogen peroxide. This is what sample data will look like when you're doing a titration experiment. Information about your volume of your sample and the concentration of your sample, if you know it, are written on the top. And then this chart is everything to do with your titrant. And so if we look at this experiment, we're using potassium permanganate. So that's our titrant. And the sample is the tin 2 chloride that's been acidified. Okay? So I know my concentration and volume, again, of the tin 2 chloride. The chart is our titrant, the KMNO4 solution. Now, when you're doing a titration, you fill your burette up close to the top. The number at the top is actually 0, and as you go down, the numbers get larger. So before you do a trial, because you do multiple trials, you record the initial reading before you release any of the potassium permanganate into your sample. So the burette, let's say in trial 1, wasn't quite close all the way at the top. It was at, you read the value exactly as it's read on the burette. Sometimes students subtract it from 50. You don't do that. You just read it exactly as it is. So the burette starts, let's say in this trial, at 1.0. They then release the solution in the burette into the Erlenmeyer flask, the 10 milliliter sample of iron 2 chloride. Iron 2 is really the SRA in this case, okay? And the permanganate is the SOA. But anyway, you release the solution, the permanganate, into the tin solution until, like I said, the color goes from colorless to a consistent pink color. Because you'll notice as you're adding drops of permanganate, it turns pink, but as you swirl, that pink goes away. You're waiting until the pink color stays, okay? And you turn the burette off and then record what the new volume is. We call that the final volume. Then what you're going to do is subtract these volumes to figure out what you actually added in that trial. So if we do that, we find that in the first trial, they added 17.40 milliliters. Now, we usually call the first trial an overshoot because what happens if what you're trying to get to is a drop-wise point where you're adding the titrant to the sample. But if you do that for the whole trial, it takes way too long. So we let the solution run really fast out of the burette, and by the time, just reaction time to close it, we've added too much. We want to get to a light pink color, not a dark pink, okay? So the first trial is just to tell us what the approximate volume is that's going to be added in each trial. So we can let it run fast till we add maybe another 15 mils and then slow it down. Now you don't refill your burette in between trials. You do dump out your Erlenmeyer flask, pipette a new 10 milliliter sample of the tin 2-chloride solution that has been acidified, but your burette initial volume is where you left off from trial 1, okay? Then you again release the solution till a light pink color is achieved, and then subtract these, and that tells you what you've added in the second trial, okay? Now remember that burettes can only hold 50 mils. So if you were to start trial 3 at 35.3 and you need to add 15 or 16 mils, you're going to run out of solution. So you refill your burette at that point and start over again, okay? But anyway, you continue to do the titration. The rule is that you continue until you get 3 trials within 0.20 milliliters. All 3 have to be within 0.2. So those are within 0.2, those are within 0.2, and those are within 0.2. They don't have to be subsequent trials, but there needs to be 3 within 0.2. So we average those 3 that were within 0.2, and we get an answer in this example of 16.80 milliliters. If you're given sample data on a test or quiz, and let's say you're given 8 trials, you do not average all 8. You only average the 3 that are within 0.2, or the 3 closest, okay? Now, let's actually go through and do the calculation with this question. So we just found the volume of the potassium permanganate. The average volume was 16.80 milliliters. That's what those trials told me. We were using 10 milliliter samples of 0.5 mole per liter acidified tin 2-chloride. So if I again start following my redox stoich steps, because titration is a type of redox stoich, I start by listing everything I have present as it would be a reactant in water. So potassium ions, permanganate ions, acidified solution means I have hydrogen ions, I have tin 2+ ions, I have chloride ions, and I have water. Okay? Identify what side of the chart they're on. Hopefully with lots of practice you get familiar with where everything is. Most positive ions are OAs, most negative ions are RAs, but there's always exceptions. Tin 2+ is on both sides. Remember Feker, Sin. Sin is the SN. Water is on both sides. Chloride is a reducing agent. Okay? Out of all of your oxidizing agents, the one closest to the top on the left is permanganate. Out of your reducing agents, the one closest to the bottom on the right is your tin 2+. So those are the half reactions I use to get to my net equation. So my oxidizing agent that's undergoing reduction is permanganate, MnO4. It's reacting with 8 hydrogen ions. Again, I'm copying this from the data booklet on page 7. It's gaining 5 electrons, and I am producing Mn2+ and 4 waters. Later in the unit, we're actually going to learn how to write these reactions from scratch. Okay, my reducing agent that loses electrons, so the electrons need to be a product undergoing oxidation, is tin 2+. So I'm copying that half reaction on the data booklet from the right to the left. I'm following it along in the data booklet. So tin 2+ on the right-hand side produces tin 4+, and 2 electrons are lost in that process. Now we balance our electrons. I have 5 and 2. So the first common thing I can get them to is 10. So this half reaction will have to be multiplied by 2. So this becomes 2, this becomes 16, this becomes 10, this becomes 2, this becomes 8. And I multiply my other half reaction by 5. 5, 5, and that becomes 10. So my electrons now balance. Okay? So to write our net ionic reaction, I have 2 moles of permanganate ions reacting with 16 moles of hydrogen ions. The electrons are now gone. And 5 moles of SN2+. This, again, I don't know if I remembered to write spontaneous on my last reaction, but don't forget spontaneity. I sometimes forget that when we're doing the stoic. We have 2 moles of Mn2+. We have 8 moles of water. And we have 5 moles of SN4+. I'm running out of room. Okay? Now we add all of our numbers. So we knew the volume of the potassium permanganate, our source of permanganate ions, was 16.80 milliliters. The concentration of permanganate is what I'm looking for. So that is my wanted. I have been given to me the concentration and volume of the tin 2+. The concentration is 0.500 moles per liter. So I'm getting all this information from up here. 0.5 mole per liter, 10 milliliter sample of the tin 2+ solution. Now, when I have a titration, oops, my stuff's popping up here. When I have a titration, if both volumes are in milliliters, I can actually leave it. And I'll show you how that works in terms of unit analysis. So my moles given comes from C times V. So my concentration, 0.500 mole per liter, times my volume. I'm going to leave it in milliliters and show you what happens. So the liters here cancel. I'm left with a millimole. So at this point, when I do that calculation, 0.5 times 10, I get 5 millimoles. So that's the prefix milli, okay? Now I keep that over to find the moles of my wanted. 5 millimoles times wanted over given. My wanted is a 2. My given is a 5. And that's going to give me, again, millimoles. 2 millimoles is my answer. Okay? Now, when I find my concentration with N over V, my N of 2 millimoles will be divided by my volume of 16.80 milliliters. Look what happens. The milli on top cancels with the milli on the bottom, and I'm left with moles per liter. So kind of a shortcut. If you want to convert everything into liters, that's fine. But I just find this to be a shortcut. So 2 divided by 16.8 gives me a concentration of 0.119. There's a 0 at the end there. I can have 3 sig digs. So my answer is 0.119 moles per liter. Okay? So titrations are just essentially a type of redox stoich where you're getting your data from a titration chart. Again, the chart's looking as follows. Go back here. Okay? That's your titration chart. You have initial and final burette readings. You subtract them to find the volume of your titrant that was added, and then use the 3 trials that are within 0.2 to find the average volume of whatever the titrant was. Okay? So again, I'll just go back there. Make sure everyone had a chance to take a look at that. And that is it for Redox Stoich. Thank you for watching this video.